Okay, today we start talking about the space of bounded variation, or the functions with bounded variations. See, the definition is given as follows. Again, we consider functions f defined over a closed interval to the set of real numbers, and consider a partition of the interval AB. We know the partition is given by a bunch of grid points such that the first one is equal to A, the last one is equal to B, and we partition this interval into several pieces. And then the variation of the function f by this partition is defined to be as denoted by this. So that means that the variation of the function f over the interval AB, and the partition is given by this delta, and it is defined to be the sum of this. So it's just like at each point, at each interval, you take the absolute value of the change of the function value over this interval. Okay, just this. Okay, and the total variation of f. The total variation of f over this interval is defined to be, it's denoted to be this. Okay, TV of f over this interval is defined to be the supremum of the variations. Okay, you can choose arbitrary partition, and you can throw it into the set. But when you take the supremum value of these variations, then this is called the total variation of f. Okay, and finally, if the function f has a finite total variation, in that if you take the supremum is still a finite number, then you call this function to have bounded variation. And we use this notation BV of AB to denote the set of functions that have bounded variations or have bounded total variation. Okay, and this is the notation we're going to use in this subsection. So I want to make two remarks. So one is that the total variation, sometimes you see that the variation is written as just TV of f. That means the interval is clear from the context, so we don't need to always write this AB over there. The other thing is that the total variation for the 1D case that we are considering here is quite different from the one that we define for higher dimensional spaces. If we have say R2 here, R2 or higher, then the definition is quite different since we cannot do partition of intervals. It is not covered in this course. I think a good reference is by Lawrence Evans. The title of the book is called Fine Properties of Functions, Measure Theory and the Fine Properties of Functions. Okay, that is and there is also the materials about the boundary variation or total variation of functions defined over higher dimensional spaces. Okay, and here our purpose is mainly to link the Lebesgue integral and the integration and the differentiation. So we only need to work on the 1D case. All right, so that's the few definitions we have. Okay, let's look at an example. We say that if a function is monotone, then it has a bounded variation. Okay, and the proof is pretty straightforward. As you can see from the definition above, suppose we have a function defined over the interval AB, and then we make some partition. So maybe the function look like this, and then the total variation or the variation of the function f using this partition is just defined to be, in this case, you can see, you can just check the value of the function at this grid points, and then you can see the length, the change here, and then the change here from this to this, and then from this to this, and then this to this. So you just take the sum of this height, and you get the variation. So I should draw it here. So there will be the total variation. The variation, and that's for this particular partition. And if you refine the partition, you will get generally you will get finer. You've got a higher value of the variation, and we'll see that soon later. But now suppose we consider a simple case, the function is monotone. Now what happens is the function generally increase, okay, like this. So when you consider the partition and then you consider the change, you see that the function value is always non-decreasing. For example, the function is non-decreasing. Then fk plus 1 or f of xi is always greater than this. It's always greater than this. The function is non-decreasing. Otherwise, it's always this is always greater than that if it's then non-increasing. Let's say that function is non-decreasing and see what happens. We'll assume that function f is non-decreasing. Then let's consider any variation. And for any partition delta, the variation of f over the interval using this delta is known to be the sum of f of xi minus f of xi minus 1. I is from 1 to n. This is the number of partitions in delta. Right? And then we know that since the function is non-decreasing, I can take out the absolute value because we know that it is always non-negative inside. So it's just this. Right? And then you can see that we can get lots of cancellations and eventually only have the first term and the last term left. So it will be fb minus f of a. Okay? And it doesn't matter which partition we have, it's always equal to this. Right? And so in this case, the total variation of f over ab is also fb minus f of a, which is finite. Okay? So that's why as long as the function is a monotone, it will have bounded variation. Okay. So let's look at another example. Actually, from the picture I showed earlier, you can imagine that if a function, in which case the function will not have a bounded variation, right? Only if that is oscillating so frequently that when you accumulate the changes, eventually blows up. Right? That is the case where the function doesn't have a bounded variation. Okay, so now let's look at another example. Suppose I have a function f that is differentiable with a bounded derivative. It's differentiable. And the derivative is bounded by m for any x. Then the function f has bounded variation. Okay. Again, we can check this easily just using the definition. For any variation delta, okay, the delta is a variation like that. We know the variation of f using this delta, right, is defined to be the sum of f of xi minus f of xi minus 1, as we defined before. And now because the function is differentiable, and we know that by the mean value theorem, this is equal to, for each term it is equal to f of, I use ci, times xi minus xi minus 1. as from 1 to n. And this Ci is between xi minus 1 and xi. Right? This is by mean value theorem. And because, sorry, this is derivative of f. So we know that the derivative is bounded by m. So each of these terms are bounded by m. So it's bounded by m times the sum of I from 1 to n, then xi minus 1. But I know that this one is greater than or equal to 0, so I can remove the absolute value. And what I will get eventually is just m times, again, I got a lot of cancellations. I will have just m times b minus a. And for every partition, I have this. So that means taking the supremum, we know that is still bounded by that value. So that means df has a bounded variation. Okay? If the function is differentiable and the derivative is bounded, then the function has a bounded variation. Okay? So far we have showed two cases where the function is nice enough to have bounded variation. Now next example is to verify the statement I just said. If the function is oscillating too much, then it could have the variation could be unbounded. The total variation can be infinity. Okay, so let's consider this example. We have a function f defined over the interval 0 to 1. It is defined by this. The f of x is equal to x times sine of pi over x if x is greater than 0. And it is equal to 0 if x is equal to 0. Okay, suppose this is the case. Oh, sorry, I'm going to show that. Then the function f does not belong to the space of bounded variations, space of functions with bounded variation. Okay, so to this end, we just need to show that total variation is unbounded, right? And to show that, we can just find a sequence of partitions such that the variation over such partitions will eventually go up to infinity. Okay, and to this end, let's just think about a partition delta k. So to think about the partition, you can imagine what kind of partition we will need. Because the function, if you plot it, it basically looks like sine of pi x is kind of like this. When x equals to 1, it is equal to 0. And when x equals to 1/2, it is you get again 0. So and it is always between 0 and 1. So I think it's something like this. So the oscillation is getting higher and higher near the 0. Okay, so that's for sine of pi over x. And then you multiply this function by x, that will just scale the values. So it's like this. Again, this is the 1. This is the 1/2. And what do you have? It just scale it. And it's again higher and higher oscillation when we approach 0. Okay, so this will be the x times sine of pi over x. So if we want to find out the highest oscillation, we can just think about choosing the point like this, right? So that the oscillation will accumulate to infinity. Okay, so let's consider the partition delta. The kth partition delta k has these grid points. So the first point is 0, second point is 2 over 2k minus 1, and then 2 to 2k minus 3. So for every fixed integer k, we're going to partition this into this interval 0, 1 to something like this. Okay, so for example, when k equals to, like k start from 2, when k equals to 2, it will partition this interval to 0, 2/3, because this will be 2/3, and then 1. Just have one grid point in between. When k equals to 3, then we have 0, 2 over 5, then 2 over 3, and then 1. Okay, so for k larger and larger, we have more and more points in between. Okay, but the key is that when we choose these grid points, we can check the value. The variation of the function f over 0, 1 using this delta k as the function, as the partition. Then we have the sum of the I from 1. Let's see how many points we have here. We have k points, right? When k equals to 3, we have, when k equals to 2, we have 3 points. So there in total will be k plus 1 points. So my I is from 1 to k. And then f of xi minus f of xi minus 1. Okay, and I know that the this will be equal to, so for the first point, I will have for the first point, I will have f of uh, 2 over 2k minus 1 minus f of 0 plus f of 2 over 2k minus 3 minus f of 2 over 2k minus 1, right? All this, all the way to the last one, which is f of 2 over 3 minus f of 1. And now just need to replace this f by the actual value we're taking. So it's 2 over 2k minus 1 times the sine of 2k minus 1 over 2 times pi. Right, that's for the first term, and then 0, which is 0 because the function was set to 0 when x equals to 0. Then we also have the other one is 2 over 2k minus 3 sine of 2k minus 3 pi minus the same thing as the first term. Okay, so the key is that we choose these points, and the last one will be 2 over 3 times sine of 3 over 2 times pi minus 1 times sine of pi. Okay, and as you can see, the first term is just, as you can see, the way we chose these points is such when you plug this back into the sine pi over x, we'll always get 1. So this is just equal to 1. This is also equal to 1. This is equal to 1. Okay, and also this is equal to 1. So we just need to is it equal to 1? Yeah, I should take the absolute value. So it should be that. Okay, we'll get this thing. So this is the, I think this is the 1 is 1. One of this is 1, the other one of this is -1. So we take the absolute value, we'll be taking the sum of the two coefficients. Okay, and also this. So eventually what we'll get is 2 over 2k minus 1 for the first term, plus 2 over 2k minus 3 plus 2 over 2k minus 1. As I said, the two signs are different, and all the way to the last term, which is this. Okay, and we can actually show this easily. You can show that this is just these two terms appeared twice. Sorry, this one appeared twice. And that's true for every of these terms. Like this one appears twice, so we'll have eventually we'll have 2 over 2k minus 1 sum for, let me use j, 2 over 2j minus 1, where j is from 1 to 2 to k, and times 2. Okay, and so for delta k, I will get this value, and you know this value is blowing up as k goes to infinity because it's basically on the order of 1 over j, so sum of 1 over j. So this one is approximately just the sum of 1 over j, j from 1 over k, and when k goes to infinity, this goes to infinity as well, right? So that's why this is blowing up as k goes to infinity. And that means I found some partition, a sequence of partitions, so that the variation actually grows up to infinity. That means the TV of f is actually equal to infinity. And that implies that the f cannot be a function of bounded variation. So this is a typical example when the oscillation is so big that when you accumulate the change, it blows up. Okay. Now, so we have several examples shown so far, and we have some rough feeling about what the total function with the bounded variation will look like. Now we are going to give a theorem that characterizes some properties of the space of bounded variations. The following statements hold. So the first one is that if f is in a space of bounded variation, then f is uniformly bounded. Uniformly bounded means that there exists some number such that the absolute value of f is bounded by this m. Okay. Second one is that the BV space is linear. The TV of f over the interval, say we have this a, b, then we have this midpoint c. The TV of f over ab is equal to the TV of f over ac plus the TV of f over cb. Okay, you can consider the total variation on the two segments separately and then add them together. If f is in BV, then the absolute value of f is also in BV. And the last one is that if f and g are both in BV, then the maximum of them, that means for each point I take the maximum value of f and g to define this new function. just still in BV. Okay, proof. The first one is pretty easy because the function has a bounded variation and it is defined as those oscillations, right? The variation is defined as this. Okay, so if the function is not uniformly bounded, then we can find a sequence of these points that the function value increases to infinity. And then we can always choose those points and then accumulate the changes, and then they will blow up. Right? So the function is bounded, has bounded variation, then in this case, the function cannot have bounded variation. Right? So if it's not uniformly bounded, then you can easily show that the function will not have a finite total variation just by choosing the points such that the f blows up. Okay, so that's first one is easy. Second one, to show the function, the BV space is a linear space, we just need to show that for any f in BV, we can show that c times f is also in BV. And that is easy. According to the definition here, we have c times f. You just pull out the absolute value of c. Right? Then nothing changed. So the CF actually has the bounded variation of CF is equal to the absolute value of c times the bounded variation, total variation of f. Okay, so that's easy. And also, if we have f and g that have bounded variation, then it's easy to show that this has bounded variation too, because again, we can just check that minus f of xi minus 1 plus g of xi minus 1. Then we can just use the triangle inequality, right? This is less than or equal to the f of xi minus f of xi minus 1 plus the f of the g of xi minus g of xi minus 1. So you know that that means for every partition, we can show that the variation of f plus g is bounded by the sum of the variations of f and g. And if f and g are both in the BV, then then the f plus g is also in BV, right? So that's easy to show. So with these two, we can show that the BV is a linear space. Okay, that's pretty easy to show. Now, the third one, let's keep it for a while and show in the end. The fourth one is also easy. Again, it's because of triangle inequality. Okay, look at this. Oh. Look at this. If I take the absolute value, will be also smaller than or equal to this. So actually, the BV or total variation of f is actually bounded by the total variation. The total variation of the absolute value of f is actually bounded by the total variation of f. Okay, but not the other direction. If we show this is in BV, it's not necessarily saying that this is in BV. Okay, a typical example is the Riemann function, which takes the value 0 when the point is irrational, and takes the value 1 when the point is irrational. In that case, or for example, no, I should consider this. It takes the value -1 when the point is irrational, and take the value 1 when the point is irrational. But in this case, when we take the absolute value, it's constantly 1. But if you do not take the absolute value, look at the original function, it's oscillating so frequently. It's easy to show that it's not in BV. Okay, so it's pretty, you can get that, but you cannot get this converse. The last one is also easy, because when you look at the maximum of a function, you can always decompose it or rewrite it as this form: f plus g over 2 plus f minus g, absolute value, over 2. The reason is that if f is bigger than g, f of x is bigger than g of x, then this f's value can be removed, and then we'll have just 2f over 2, which is just f when f is bigger than g. Right? Otherwise, you get g when f is less than g, greater than or equal to less than 2. So in either case, this is just equal to the maximum of f and g. Okay, so we know that if f and g are in BV space, then this is in BV because it's a linear, BV is linear space. And I also know that this is in BV space because f minus g is in BV, and the absolute value of that is also in BV because of that. So then you have two BV functions. Take a linear combination of them, is still in BV. All right, so that's how we show this last one. So the only thing that we haven't showed so far is the third item, the third statement. Now let's show that. Okay. We need to show that the left-hand side is smaller than or equal to the right-hand side, and then we show the right-hand side is smaller than or equal to the left-hand side. Okay, so to show that, for any partition delta of AB, we know that the variation of f with this delta as the partition is smaller than or equal to the partition with an additional point. So I use this notation, means that if C is already in the partition, is already a grid point in the partition, then we don't change it. But if it's not, then we just add it. Okay, we'll insert one more point. But once you insert one more point, the variation will be increased. The reason is, you can think that if I zoom in, say for example, if this xi minus 1, this is xi, and I add one more point C here. So this A will be here, this B somewhere here. So when I add this point, add one more point, then originally this part I only need f of xi minus f of xi minus 1 for this interval, over this interval. But now since I have one more point in between, so this I will have this f of xi minus f of c plus f of c minus f of xi minus 1. And apparently the first line is smaller than the second line due to the triangle inequality. So that's why when you add this one more point into the partition, the variation will not decrease. Okay, and that means that's the reason for this inequality. And then once you add this C, you can the variation can be separated because we can also consider the interval or the intersection of this delta and the interval AC. So this is equal to the variation of f with AC on the AC, where this partition is also said to be the intersection of the delta and AC. So by this term, I mean the using the grid points we have from delta, and but only look at those points falling into this interval AC. Okay, so it's like that. I have this A, B, and I have some grid partition points, and now I add one more point C here. Then I just look at this, the interval AC. This still has a partition that we have from the delta. Okay, so that's why we can rewrite this to be the sum of these two. Okay, and you know that since this is the anyway a partition of the interval AC, so that means it's less than or equal to the TV of f over AC, since the TV is the supremum of the variations. Similarly, the second term is bounded by the total bounded by the total variation of f over the interval CB. And now we show that for any partition, it is bounded by that. Then we take the supremum of the left-hand side is still bounded by that, but the supremum of the left-hand side is equal to the TV of f over the interval AB. So that apparently is more than equal to that. Okay, so we showed that one direction, that the left-hand side is smaller than or equal to the right-hand side. Now let's show the other direction. Okay. Because the right-hand side, we know that is total variation. The total variation is taken as the supremum. So then for any epsilon greater than 0, we know there exists some partition delta 1. So this is the partition there exists the partition delta 1 of the interval AC such that since TV is a supremum, so I know that there exists a partition so that the total variation of f over the AC is smaller than the variation of f over AC using this delta 1 plus epsilon over 2, right? And similarly, there exists also a delta 2, which is a partition over the interval CB, such that the TV of f over CB is also smaller than the corresponding variation using the delta 2 plus 1/2, half of epsilon. Okay, and this means that when we combine these two partitions, we know that it is a partition of the whole interval AB. We know that because you do the partition over the delta 1 over this interval using delta 1, and you do the partition over this interval, and then you just combine them, you get a partition of the entire interval AB, and the variation will be just the sum of these two. That's really easy to show. So what we get is that the TV of f AC plus the TV of f CB. Let me move the epsilon to the left, so it will be minus half epsilon, another half epsilon, so that will be just epsilon. It's more than the variation of f over AC delta 1 plus the variation of f CB delta 2, and that's we just said this is equal to the variation of f over the AB, where the partition is given by the union of the two partitions, and because this is smaller than the supremum, which is the TV of f over AB, we show that this is true. And now this is true for every epsilon. This is true for every epsilon. So that just means the TV of f AC plus the TV of f CB is actually smaller than or equal to the TV of f AB, because epsilon is arbitrary and positive, right? So that's how we show the other direction. So now we show the both of the directions, then that claims this. Okay, so that's the proof. Now let's look at the geometric interpretation of the total variation. So as we said, the total variation function with the bounded variation or total variation is finite means that the function doesn't have too much oscillation, and this can be characterized by the curve or by the piecewise linear connection between the points we have for the given partition. So what I mean by that is you look at the interval AB, and you have this function depending on AB, and then you can partition it. So this is x1, x2, x3, so on and so forth. And let's look at the grid points and the corresponding function values. We can make this kind of connection, piecewise linear connection of them. So the function has a total variation. The variation under this partition is actually bounded by the total length in here. In some sense, let me show you what exactly that means. And then with that, we can also show that the function has a finite total variation, means that when you, no matter what partition you have, the total length for this kind of thing will be bounded above, okay, or taking the supremum of the length over the all the possible partitions, the length is still finite, so they will be equivalent to the function having a finite total variation. So let me expand that. Maybe it's better in this sentence. So for a partition delta, which is like this, let's consider the points on the curve. This is what I just draw on the right. Consider point x naught, f of x naught. This is actually the first point right here. Okay, and then we also have x1, f of x1. That will be the value here. Okay, just consider those points up to the last one, which is x0, xn, f of xn. And now we can draw the line connecting them. Okay, draw the lines, piecewise linear lines to connect them. Then the total length of the lines, like I draw here, this plus the length here plus the length here. So we know that the total length, I use the notation L to denote the length of this piecewise linear curves, and that will be equal to, as you know, that this will be equal to the sum for I from 1 to n, and connecting these 2 points, for example, the length will be this minus this squared plus this minus this squared, and then take the square root of the two terms, sum of the two terms, which is in general the xi minus 1 squared plus f of xi minus f of xi minus 1 squared, and then I take a square root. Right? So that's the total length. So this is, each of this is the length for each piece, but the total length, which is taking the sum of them. And you can see that when I have, say a squared plus b squared, take a square root, I know that this is bounded by a plus b. You can easily show that because you can just take the square on both sides. You can see that this inequality holds. So this also means that this is bounded by the sum for I from 1 to n, and the inside will be xi minus 1 plus f of xi minus f of xi minus 1. Well, the second term is exactly the same as we used for the variation, but the first term, you can see that the first term, this is always non-negative. So I can remove the absolute value as we did earlier, and then just get this b minus a term out. And the rest will be still the same, which is this f of xi minus f of xi minus 1. Okay, and this side is just the variation of f on the AB using the delta as the partition. Okay, so that's why we show that the total length here is just bounded by that value. On the other hand, we also know that this is greater than or equal to just this term only inside, just square root of this second term only. But then we can remove the absolute value, or remove the square root, and we'll cancel the square root and the square. We only have this f of xi minus f of xi minus 1 absolute value. So that means the L delta of f is actually bounded in between b minus a plus the variation of f over ab using the delta. On the other hand, is bounded below by this variation of f over the interval ab with this delta. All right. So with that, you can see that this quantity is somehow bounded in between these two, and this is just a fixed number. So when you take the supremum of this value, you can see that the left-hand side becomes the TV. Okay, it becomes the TV of f, and the right-hand side is just become b minus a plus the TV of f over ab. So over ab. Okay, so that means the supremum of this delta L delta f is just bounded in between. Okay, so we call this one to be L of f. So you can see that the function has a bounded variation, or the total variation of f is finite if and only if this quantity is finite. Okay, and this is just the supremum of this length, or the supremum of this quantity, and the supremum is taken over all the partitions. Okay, this is another interpretation of the total variation. It's just that this kind of length, we look at the zigzag length. For any function, you can just look at this length, and when you get a refined partition, they can still calculate the length. If the length doesn't blow up, then we say the function. That means the function has a bounded variation. All right, so that's the interpretation we just had. And let's look at another result. So this result is due to Jordan. What it says that this is a very interesting result. This says that if the function has a bounded variation, if and only if it can be written as the difference of two non-decreasing functions. Non-decreasing functions. G and H, such that f can be written as the difference of them. Okay, so that's pretty interesting. That gives us a full characterization of functions with bounded variation over the interval. Okay, it just need to be written. It can be written as the difference of two non-decreasing functions. This choice of these non-decreasing functions will not be unique because you can always add the same constant or same function, the same constant value to both of these two terms, and then we take the difference. The constant will be cancelled. So the choice of G and H is not unique. But we just need to show that there exists one. Okay, so to show this, we need to show both directions. first let's show that this direction. So suppose the function f is in BV. Well, it's in BV, so we can define or denote this T f of x to be this, to be the total variation of f over the interval ax. Okay, so the x is moving on this interval. Okay, so it's this x. So the Tf of x will be just the total variation of f over this interval. And as you can see that when we increase x, this Tf of x will increase, right? Because we have more intervals, then we'll actually just accumulate. The oscillation will be further accumulated, right? So when x increases, this Tf of x also increases. So it is a increasing function. Okay, and it is also finite because it's a increasing function, and the maximum value of this function is bounded above by. So we first know that this is always true. And also that the Tf of x is bounded by Tf of b, but Tf of b is just the Tv of f over the interval AB. Okay, and since the f is in BV, so we know that this is the bounded value. So that means this is always bounded above by that. Okay, so I know that. And now we just define, we let this g to be, gx to be 1/2 of T fx plus f of x, and also let g hx to be 1/2 of T f of x minus f of x. Okay, and then we can show that both of these two functions are strictly increasing. The reason is, for example, for gx, for any x smaller than y, the gy minus gx, we just need to show that this is greater than or equal to 0, right? For any x smaller than y, we just need to show that this is greater than or equal to 0 for g to be non-decreasing. Okay? And according to our definition, this is the 1/2 of Tfy minus f of y plus minus 1/2 of Tf of x plus f of x. And now I combine these two, which is Tf of y minus Tf of x plus 1/2 of f of y minus f of x. Okay, so it doesn't matter what the first term is pretty easy to show this because the according to our definition, the Tf of x is just the Tv of f up to the point x, and then Tf of y will be Tv of f up to the point y, a to the y. So the difference of the two will be just the Tv of f over the interval x to y. That's because of this third property which is proved. If we replace this as a to x, then x to y, then this side will be a to y. Okay, so that's why the difference of them will be just the Tv of f over the interval x to y. So this is just the 1/2 of the Tv of f over the interval x to y. And this second term, I know that is either positive or negative, but it must be greater than or equal to, sorry, this must be greater than or equal to the negative of the absolute value, right? So that's why I can replace this by that. is minus 1/2 of f of y minus f of x. Okay, and then you can show the reason is that this is greater than or equal to this, right? Since this is the most negative value you can get. And you can realize that this is just a partition of the interval, just using 2 points, the x and y. So this is definitely smaller than this, since total variation is a supremum of the variations, and this is just a specific instance of variation. So that's why this must be greater than. This must be greater than or equal to 0. Okay, and that shows that the g is non-decreasing. And similarly for h, then we'll have minus here, also minus here, and then you have minus here. But again, if it's minus, it's still bigger than or equal to this quantity, and it's still greater than or equal to 0. Okay, so the g is non-decreasing. And similarly, the h is non-decreasing. And now we can see that the difference of g and h, we just take the difference of these two, we'll just cancel out this term. And then we'll just have f, right? G minus h will be f. Okay, so that shows this direction. The other direction is simple. If we know that f is written as, if f is written as to the difference of two functions, then if g and h are monotone, so let's say non-decreasing, just write it in this way, then according to the result, the example, first example after the definition, we know that the g and h, they are both in BV of AB, right? And then because the BV space is linear, so we know that the g minus f, g minus h is also in BV. And that means that f is in BV, since f is known to be the difference of g minus h. Okay, so this shows that the f, if f can be written as the difference of two non-decreasing functions, then f must be TV. Right, must be in TV. Okay. So next, let's let's show a lemma for our the Mill theorem we have below. So suppose the f is a Lebesgue integrable function, and we define f(h) to be that. So I'll explain what this one is. X plus h f of t dt. Okay. So our function f is only, little f is only defined over interval a to b, but this could go beyond, this value could go beyond b. For example, when x is close to b and h is a little bit big, then we probably will take integral of f over somewhere outside of b, on the right of b. So in this case, we just assume that the function takes the constant value f of b when x is bigger than b. Okay, we assume f of x is equal to b if this x is bigger than b. Okay, and similarly, the h could be negative, so let's also assume that f of x will be equal to a if x is smaller than a. Okay, if h is, in case h is negative. Well, we only consider the positive case here. Yeah, because in that case you can just replace x by x minus h. Okay, that will be not cause any confusion. Okay, and the conclusion we want to make is that the limit for h going to 0, the limit of this f of a the interval of a to b, f h x minus f of x, we want to show that this is equal to 0. dx, this is equal to 0. Okay, so now before we prove it, let me explain what this one is. So this is like for every x, I'll consider the average integral of the function f. So the f could look here like this. So the integral we have here is just the area, right? It's like the area here, and divided by h, we just normalize it since it depends on how large this interval is. So that's my fh. Okay, and you can imagine that this fh is pretty close to f of x when h is small, right? It should be pretty close to f of x when h is small. And how close it is, it can be interpreted in this way. When we take the difference of this function, new function, capital F, h, take the difference of this and f, and take f's value, take the integral, and then this integral actually approaches 0 as h goes to 0. Okay, and that makes sense because when h is getting smaller and smaller, this is almost like just almost like look like f of x. Okay, but how to show this formally? So the proof goes like this. Because this f is integrable, okay, so we know that the continuity of integrals, we know that for any epsilon greater than 0, there exists a delta such that the integral of f of x plus h minus f of x will be less than epsilon for all the h between negative delta and delta, right? So we know by continuity of integrals, we know this can be, for any epsilon, we can choose the delta such that this is smaller than epsilon, right? On the other hand, now let's consider the integrand for the integral we're trying to prove the limit. So let's look at this part. The fh of x minus f of x, what this one is, according to our definition above, we can always think this as a, let me see how we do a change of variable. This first term which can be written as over h times 0 to h f of x plus t. Right, I still used t here. I can use the other notation, for example, as. So t is from x to x plus h. Then I just put x inside. No need to put the x in the limits of the integral, right? So we can always write this. This is equivalent, just do a simple change of variable, and then minus f of x. And this is equal to what? This is the constant over when we are taking integral with respect to t. So this can be written as the f of x times dt 0 to h divided by h here. The reason is the f of x is just constant. It can be pulled out, and then the integral is just equal to h. So it cancels with the bottom, h on the bottom. So that's how we can write this in this way. So then, since both of them can be written as integrals, so I combine the integrand, I will have this minus f of x dt. Okay, so we know this. There is, when we take the integral right now, as we are trying to prove the limit of this integral goes to 0. So this integral of that dx. So now just look at the integrand. The integrand is equal to 1 over h, 0 to h, f of x plus h minus f of x dt dx. And you know that when we take the integral, absolute value of the integral is less than or equal to the integral of the absolute value. So I have this. I can put the integral inside, absolute value inside. Then I'll get this inequality. Okay, now we have a integral. Sorry, I have t here. T here. So now I have an integral of a non-negative function. I have an integral of a non-negative function. So by the Fubini theorem or the Tonality theorem, we know that you can freely exchange the order of integration. So I can exchange the integration order. I take the integration with respect to x first, then with respect to t. So in this case, h is t is still from 0 to h. We have 1/2 times h. And I have the integral ab f of x plus t minus f of x dx, then dt. Okay, so I can exchange the order. Now we can realize that in here, when h is small, when h is small, we know that this one, see, since t is between 0 to h, so I know that t is smaller than h. So when h is less than delta, I know that t is less than delta as well. And that means this quantity here is less than epsilon. Okay, because we show that as long as h, the absolute value of h is less than delta, then we have this. We will have this. We will have this, right? So the t is one of such value. So that means this is less than epsilon, and this is less than epsilon. So that means this is less than or equal to epsilon times, it's a constant, so I can pull it out. And also the actually 1 over h is also a constant, so 1 over h. And 0 to h, then dt. But the integral here, they will be just cancelled. They will be equal to 1, so this is just epsilon. Okay, so we show that for any epsilon, there exists a delta such that when our h is smaller than delta, the this quantity here is less than epsilon, and that just means the limit of this integral when h is going to 0, this limit is just equal to 0. Okay, so that completes the proof. Okay. All right, now let's show the Mill theorem of this section. The way it says is, suppose that I have function f that is integrable. Then we define the function f of x, which is the integral of indefinite integral of t dt up to the point x. Then the derivative of f is equal to f almost everywhere on a, b. Okay, so now we this is actually trying to connect the fundamental theorem of calculus, since we know that when I have a function that is integrable, then we take the indefinite integral, we get this f, and then hopefully the derivative of f, derivative of this capital F, gets back to this integrand. Right, so that's the Mill theorem that we want to prove now. And this proof itself is pretty easy. The reason is, since we look at the f prime, this is the limit of when h goes to 0. This is the limit of, according to our definition, it should be f of x plus h minus f of x divided by h. Right? That should be supposed to be the derivative. But now recall the definition of capital F. The f of x plus h is just the a integral of a to x plus h, f of t dt. And the second term, capital F of x, is just the integral of little f from a to x dt. But now you can see that these two, when you take the difference, it just become the integral from x to x plus h, f of t dt. And then we have one more 1 over h outside. So that's essentially just the f h of x. Right? Because we define this whole thing here to be the f sub h of x. That's what we defined so far. Right here. Okay, so that's the derivative of f is just equal to that. And now we can easily show that the limit of this fh, which is just the derivative of the capital F, is equal to the little f almost everywhere. To show that, we just need to look at this. If we can show that this apparently is greater than or equal to 0, if we can show that this is the less than or equal to 0, then we'll prove that this integral of this is equal to 0, and that means the integrand is equal to 0 almost everywhere, right? So as long as we can show this is smaller than or equal to 0, you'll be fine. So remember that this inside is just f of x minus, as we said, this limit for fh of x, h going to 0. Okay, and this is apparently is equal to the limit of f of x for each fixed x, just the limit of that. And according to the Fatot's lemma, this is less than or equal to the lim inf of h going to 0, ab f of x minus this. But we just show that this goes to 0, right? When as h goes to 0, this limit actually exists and it goes to 0. So that's why this is equal to, it's less than or equal to, but actually it's equal to 0. Okay, and on the one side, we know that this is greater than or equal to 0. On the other side, we saw this, so that means fx minus f prime of x is equal to 0 almost everywhere, and just means these two functions are equal almost everywhere. Okay, and that completes the proof.